Hey everyone. Just get things a little set up. I think I'm getting good at this though. I think this should only take 2 minutes, which I'm pretty impressed with. But I guess before I say that, let me make sure it's actually working. Okay. So up on Twitch, up on YouTube, are we on X? Yeah, it seems like. Okay, cool. Okay. Okay. So we got some pretty exciting. We got some pretty exciting things that we've been working on. I think I'm going to show off one of the new features. The new feature, just on today's daily question, the Harvard Sigmoid function. So we basically have a new notebook functionality, which I think is better than the regular, solving a question. It gives you the starter code here, and it gives you 2 test cases. So test case 1, test case 2. I think the benefit of this, let me just 7, we'll solve it in a second, but it's a lot faster, and you could iterate a lot faster through these questions and test things out a lot faster than theoretically going here and running code and have to wait. Like, this is a lot faster in terms of your results. We're still improving it. Like, one thing you note, like, it will, like, this code doesn't get saved, so it's a little stressful. But if you actually submit the code, it will be saved in submissions. So, but yeah, this just allows you, pick another cell, just image 10, high. And then it breaks, because I misspelled range. But this is a lot faster way of iterating through this and really solving the question. And I feel like most people in the machine learning, AI, data science field are very used to notebooks, so I hope you guys enjoy it. Let's solve this question. I actually don't know what a hard sigmoid function is. Let's go to then regular sigmoid. I guess regular sigmoid. Start there. Regular sigmoid looks like an S. Well, not actually like an S. Not that much like an S. It's maybe that more. And it converts anything, all numbers from the range 0 to 1. Yeah, so basically converts numbers into probabilities. I do quote unquote, it's not like truly probabilities, but it has the feature of, the lowest value is 0, the highest value is 1. That's regular sigmoid. Let's learn about what hard sigmoid is. And the sigmoid activation function is computationally more efficient than standard sigmoid function while maintaining similar characteristics. This function is particularly useful in neural networks, blah blah blah. Okay, this is the main crux of it. If x is less than 2.5, it's 0. If x is between this to this, x is. Okay, is it as simple as that? I'm gonna start coding and see what happens. If x is less than equal to minus 2.5. if this is greater than negative 2.5 and x is less than 2.5. I wonder how they came up with the way to put the greater than and equal to. Like, it's 1 if it's greater than or equal to 2. Like, it feels like just a random random choices are being made, but maybe I'm wrong, or maybe there's some more thought into that process that I don't understand. Turn 0.2 times x plus 0.5. I feel like a lot of people do this. I'm very lazy, so like I'm saying, they add the 0 at 0.5. I just do 0.5. I feel like I don't see this a lot for some reason. I feel like most people add the 0 in. I don't understand why though. Okay. So now instead of running through, all of the test cases, I could just run this. It could tell me, hey, you're an idiot, and I'll be like, that's not nice. What did I do? Still upset at me? Are you still upset at me? No. Indentation error. We're going to have to deal with indentation errors. Maybe I have to fix that. Okay, I'm gonna have to fix the indentation issues because that's always annoying. But in general, we can run this. Okay, we can run this. We get 0.62, which is the expected output. We can run this, which we would expect to be 1, and it is 1. We can make our own new, let's see. If I do -3, I'd expect the output to be 0. Cool if it was between, what is it, 2? So let's say, let me check an edge case. If it's 2.5, it should be 1. And it is. I'm saying you could just iterate a lot faster through this test. Edge case is more, and then when you're ready, you basically submit. Just go to the bottom, and it will run through all of the test cases that we have available for this question, which might not be so many. We do need to add more for. Oh, I got something wrong. Annoying like that. It's supposed to be a float. 1.0. Is that? I love when I get upset at my own site. I'm like, wow, what a stupid idea. What a stupid implementation. And I'm like, whoever made this is an idiot. And then I'm like, wait, I'm the idiot. It's not as fun. It's not as fun like if I go on LeetCode or something and there's an issue with their class. I'm like, wow, so stupid of them. And it's on my side. It's not as fun to complain about because I just feel like it just gets me stressed that like, oh damn, we got some more work to do. But yeah, so we got it correct. You know, we got the little check thing there. Now we have the solution actually in our code. So even if we lose this, we still have our solution. Okay, go back here. I don't know if it actually updates back in here. It does not, so you have to. A little annoying, but again, we're working on a few of the bugs, but I feel like in general, you know, this will improve people's enjoyment of solving these types of questions. And if it doesn't, then I was wrong and whatever, but I'll enjoy solving questions with the notebook feature. Let's see if we have any comments or anyone's thoughts on these things. Okay. Seems like good. Seems like people understand it to an extent. So this is notebook mode. We also have it available for labs. Side note. Let's see if I've already on a side note tangent. We're doing a competition for this question. I posted it on X somewhere. Basically, if you solve this question, you get over 85% accuracy, and post it on, basically make a post on X or LinkedIn and tag us saying like, here's my ranking, here's proof that I actually got over 85% accuracy. You'll be entered into a competition to win either a t-shirt or a pair of shoes. You're like, why? Like, I don't know. And these shirts, I enjoy them. I don't know if you can see this, but I have two of them. I have the blue one and the green one, and I like them. They're pretty good quality. And like these are stitched in, so it, you know, it's not just printed on. I do not own a pair of the shoes. If someone wins this and wants the shoes, you know, let me know and I'll send them over. Please send a picture of you wearing them. I maybe for the holidays I'll end up buying myself a pair of these. What's his name? I always get lost in. Here, notebook mode is similar. This, we have some of our test cases. The question here is basically based on micrograd, on Andrew Karpathy's videos. If you haven't watched them, go watch them. They'll explain it. I'm sure my learn section is fine, but he explains it like a god. But yeah, I'd say watch that video and then try and solve this question, because you could watch a video and be like, yeah, the whole premise of my site, I feel like, is a math class where, you know, when you watch your teacher, you know, doing something on the board and you're like, oh yeah, this makes complete sense. Then you go home and you try to do your homework, you're like, oh, I understood like 20% of that. So the goal of DeepML is, you know, like, you know, everyone thinks they know something. Oh yeah, I know how Transformer works. Okay, implement it with just NumPy, see how much you actually understand and see how much you actually don't understand. But yeah, so this is basically saying implement an entire neural network, you know, the forward pass to the backward pass from scratch. So I'd say watch Andrew Karpathy's video, micrograd. Sure, 90% of you know about it already, if not more. And then I'd say try to solve this question. If you want to be part of the competition and win a t-shirt, have a chance to win a t-shirt or a pair of shoes, post it. If not, then it's just good for learning. Today, we also, on our Discord, we have a paper review. I'm a little behind on it, so I decided just to stream myself reading the paper, and you know, let me know if you guys have any questions or thoughts about it. One thing I guess I'll mention. Sorry, I was just checking my phone. Seems like someone had an error on. Yeah, seems like someone has an error on something. I need to go through this later, but right now I want to try and stick to this and finish reading this paper, and I'll fix any other issues we have, I guess, a little later. So the reason, oh, hey, I saw someone say hi on YouTube. What's up? So we're gonna review this paper. The reason I want to review this paper is I don't understand, because right now my understanding of optimizers is, we have basically hand-drawn optimizers. Like you have simple gradient descent, where you have your weights, and you're taking your old weights, subtract from the learning rate times the gradient. Like, this is basic gradient descent. It might be better than you. I think at some point I made a meme like gradient descent is smarter than you, or I have some swag on our site that says that. It's probably smarter than you in some aspects, but not in others. And then, we have our variance, we have atom, we have momentum, there's like 5 other optimizers. And one question I always had was, not always, but recently had, was why are we hand drawing these features? And then that got me thinking about, okay, when are humans better than LLMs? Why are they better than LLMs? And in my mind, humans are better than LLMs at generalizing. So we're good at taking some information. Like we're really good at new tasks. Like we don't need a million images of the number 2 to understand at number 2, this is a number 1. We could look at like 3 images, tell a kid like, hey, this is a number 2, this is 1. Tell them a few times, like I got it, I don't need a million examples. So my question was like, why are we so much better at, why do we need such a small number of examples, but, algorithms, and neural networks, and billions of dollars of research go into this, and they need, thousands. I'd say thousands, some need more, depending on the issue, but, or to play chess, you need whatever. And then I feel like the solution usually people give for this, I'm trying all of this stuff, but the solution people usually give is, we're pre-trained. So when you're a kid, you learn about a lot of things. You learn about shapes and colors, and you're just looking around, and you're basically constantly learning. You're not just given the task what's 2, what's 1 from like random weights. You have like pre-trained weights, and you have pre-built learning mechanisms, and like kids are just in general, like the reason they're so smart and so good at generalizing is because they have a lot of pre-training on, let's say, unlabeled data. So then I was thinking, it's basically, in my mind, we have an optimizer. Like, I guess humans have an optimizer. But we're really good at optimizing because I'm trying to think how to put this in a nicely framed sentence. We're really good at optimizing because we see so many situations. And we go through so many issues, and every issue it's not the same. Playing chess and playing checkers are different things. But our weights, like once you're able to play checkers, you understand. Okay, this is a board. This is how pieces move. Pieces move differently, and we can generalize that information to chess. Obviously, not perfectly, so we need to learn how the pieces move and things are different, but it's relatively quick. So in my mind, we all have, we have a better optimization algorithm than neural networks. So I don't understand why we're all using hand-drawn things from, we'll retrain an optimizer from scratch every single time. And my hypothesis, I could be easily wrong, and I'm sure people can tell me why I'm wrong, maybe. If you do, please let me know. Why do... My hypothesis... got lost. Why do we... I'm trying to think where I was going with this, and it was a really good point. Basically, we could go from something hand-drawn like this to something... this is usually how things go. We go and we optimize it using machine learning, and we build better, more robust systems. But why don't we have an algorithm that could... I'm assuming that a lot of tasks, like we have a lost landscape, so this is a lost landscape. Let's say this is MNIST lost. MNIST. I'll try to go this quickly because I actually want to read the paper. And then this could be fashion MNIST. And they're obviously not going to be the same. Things are going to be different. There's different structures of the lost landscapes. Like, everything will be different, but I'm assuming there's some commonalities from this lost landscape to this lost landscape. And if we were able to train an algorithm to optimize our gradients more efficiently, and basically, let's say we trained it on 1,000 tasks. I think the 1,001th task, it could optimize, like, it could learn, like, oh, this is a typical lost landscape, and oh, okay, I can move a little faster and move the gradients a little more here, move them less here, like, basically get a better understanding of lost landscapes and being able to update it more efficiently. This way we don't need to start from zero consistently, because, and this could go from model to model, like, there's very few things like that. The only things that, are the same in models are either optimizers or loss functions. Optimizers are, and we can't really have loss functions that learn from each other thing. Like, that doesn't really make sense. We could go with the optimization route. If we have an optimizer that basically was trained on 1,000 tasks, or 1,000,000 tasks, I don't know, we have a bunch of data sets, on Kaggle and stuff like that. I feel like we could make these models, we could make them learn a lot faster. And there is transfer learning, but transfer learning works with, you need similar architectures, or you need to be able to move the weights efficiently, and there's a lot of things that are very annoying about that. But if you have an optimizer, and it's just... that's my current thought process on optimizers. I could be easily missing something, and I'm, let me know if I am. But yeah, so after the rant, we're gonna get into the paper. And this is from 2016. I think there's some more recent papers about this topic, but this seemed pretty interesting. See, this sentence incorporates my last, 15 minutes or whatever it was pretty well. The move from hand-designed features to learned features in machine learning has been widely successful. In spite of optimization algorithms are still... Yeah, so it's basically like... we're still using hand design features. We're still using hand designed optimization algorithms, which feels like it doesn't make so much sense. I feel like I'm not gonna go into it because I want to go through the paper, but it's not. I just made a tweet about that. It's not very bitter lesson. Bitter lessony. I don't know. Because we're hand drawing, we're hand coming up with these optimizers. We're not using any compute. It's not getting better as compute gets better. It's not getting better. Like if you're able to train a model and improve these things, I just don't see why. I'm sure there's a reason, maybe. So here, okay. So here they're trying to make an optimizer that can learn from the problem, allowing the algorithm to exploit structures in the problem or interest in. Okay, so it's saying, yeah, we want to basically train an algorithm that does gradient descent. So gradient. Also, this is a hilarious name. I like this. Another reason to read it. So it's from 2026 because they're using LSTMs instead of transformers. I haven't seen the word LSTM in a while. They're saying it outperforms hand-drawn optimizers. Also, like this, like neural arts, like I'm assuming it's like style transfer was a big thing back in the day. Now I feel like there's no style. Maybe there is. Actually, I have no idea. Maybe people. What if people still like work on style transfer? Let's see if they have. They should like had. For all the newer people in machine learning, yeah, style transfer. This was good times. Basically, you had two images. You had the main image, and you had what you wanted to be styled like, and sort of took the main image and drew it in the style. So now I feel like you just ask ChatGPT, hey, make this in the style of blah, and it does it. But I wonder, like, are people still working on these types of algorithms? Do they work better than ChatGPT's? Does ChatGPT just call a model that does this? No. I guess no, it does not, because it's more generalizable. Like, I wonder if you do a model specifically made for this, will do it better. But back to the top. We got a lot of fun ahead of us. Okay. Introduction. So typically, optimizer is an objective function f of theta. Theta is the weights defined over. Okay. The goal is to find. Oh, I guess that's the loss. Yeah. So given these weights, this is the loss. So you want to minimize the loss by editing the weights. That's our goal as gradient descent comes. Okay, so this is pretty much gradient descent. It is, but gradient descent, it's basically saying we take the old weights minus, so these new weights, old weights minus the learning rate times the partial derivative, the gradients we'll call it, in regards to the loss function, and this is how we would get our new thetas. From vanilla gradient descent, however, so this is saying the issue with gradient descent is it only uses the first order derivatives, it doesn't use the second order derivatives, getting the curvature of the current point. I forget. I know there's a reason we don't use Hessian matrix or second order derivatives. I don't remember it, to be honest, but I remember it was a good reason. It's talking about how there's a lot of different types of hand-drawn optimizers for different fields. There's different types of optimizers. Momentum, Atom, sure. Atom has been around for a while. And I feel like it's still widely used today. I mean, there's some newer things, but still widely used. It's saying in different communities they have different optimizers. So, focus on trends to favor very different optimizers. It's interesting. It'd be interesting going into a different field and seeing what optimizers they use. See how similar they are to the ones in deep learning, because I have no idea what's the other optimizers. I'm saying different communities have different optimizers to take advantage, I guess, of the different law structures. But they usually don't do great on out-of-scope things. Probably should know what this is. More of a no free lunch theorems for optimizers, blah blah blah. Setting up combinatorial optimizations, no algorithm is able to do better than a random strategy in expectation. So saying long run they'll all be the same. This just that's interesting. So this is saying because maybe I need to know more about this, but saying people have to make sub-algorithms for problems because in expectation that everything would be as good as random. Let's go. No one uses, like, if there's a person out there that is in tech that doesn't use ChatGPT or any LLM provider at all, I wonder what's that percentage. I'd imagine it's pretty low. Because I feel like even just to explain things like this is pretty great. Core idea. Average over all possible problems, no optimization algorithm is better than any other. Why is this true? That's a good point. This. Okay. To me, I'm pretty shocked by this. Why is this true? Both randoms graded in smooth continuous landscapes. There must be some extremely fine landscape where Adam is worse than a random guess. Okay. Okay. That's interesting. So I guess given a complete but I guess usually uh, machine learning and deep learning data sets and problems are usually a little more smooth landscapes, if I'm not mistaken. I want to read a landscape paper. I'm pretty sure it's a thing. If anyone has any recommendations, let me know. It's not say all optimizers are the same in real life. Yeah, I mean, my whole thing is like, hey, there's definitely patterns in these loss functions amongst different tasks, amongst different architectures that can be exploited on this. And why are we doing it hand-drawn? What's a different instance where you'd use an optimizer? Like, only kills the idea that a universal best optimizer for every imaginable function. Okay, I mean, but can I have a universal best optimizer for all machine learning functions? I guess all real, because I'm assuming there has to be some underlying something. There's some underlying, I mean, we're proof of that there's some underlying mechanism to these loss functions that we can pick up things relatively quickly. Like, you know, we don't need so much data. We could optimize our loss for something relatively quickly. Obviously, maybe to get like really good, we actually need to like start doing slower steps, but we could get 70% of the way there pretty quickly. Like if you learn chess, I'm sure you could pick up the basics relatively quickly. You probably can pick up the basics faster than an algorithm. Just check. Okay. That's interesting. Like, I don't know. It's cool. Maybe, you know, there's the new optimizer, Muno. I don't know how to pronounce it. It's N-U-O-N, M-U-N-O, something like that. That's pretty useful for LLMs. So maybe, yeah, that fits the bill there. Okay, but I guess we don't want to do the best on all functions. We want to do the best on all real-world scenarios. Which sounds like a lot, but I'd imagine it's a small subset of all mathematical functions. Why don't I do this quickly? I try to find a video. Usually I like to watch a video just to understand the concepts on a high level. Just do this. Just to understand the core concepts, and then we'll continue with reading it. Here's a simple explanation. Write it. Just me. I don't want it in terms of in terms of, you know, free lunch stuff. No. No, don't. I don't want to know free lunch thing. go over is this. So traditional optimization works like this, correct? This design engineered by humans does not adapt to specific structures of the problem. Whatever. Okay. Key idea. Optimizers. Optimizers in a neural network. LSTM. Okay. Okay, so this is the interesting part. So they're taking the current gradients. Let's draw an LSTM. Draw the current neural network. So we have. So we have, I guess, the current gradients into the model. I'm assuming it's gonna look. I mean, this is what the RNN looks like. So let's continue reading it. Reading the current step. Okay. Its own internal memory state. So yeah, memory H. And it takes gradient at the current step, cool. Its own internal memory state and outputs. The update of the parameters. Okay. So for the new step, we would have, okay, so it's just trying to, maybe this is the old weights, so we're just trying to add the, okay. So we're taking in the gradients and we're trying to shift those gradients. Oh, that's interesting. So I guess we're just trying to shift those gradients and get the output from here. So output would be, I guess, a new brand. Have an LSTM question on DeepML. If not, I probably should add one. It's annoying, and you probably will never use an LSTM, but it's a good understanding of the fundamentals. So I'm guessing, yeah. So. Here it looks at the gradients. Let's use gradient descent to train this LSTM, which is gradient descent by gradient descent. Gradient descent by gradient descent. But here, I guess it would take in the gradients, make the output, and then get the loss from the bigger model. At least that's how I would do it. And what I think they're doing, I train the optimizers again. The optimized optimizer using another optimizer is an atom. Sample a task, like quadratic functions in a small image network. Okay. Unroll the optimizer for T steps. So basically we are going some model. Inputs, and we want, and it's output, and then we use an optimizer to use optimizer to optimizer. Let's go back to the model and teach the model. So I'm guessing we do this a whole bunch of times, and now so we do that a whole bunch of times. each step, we're optimizing it more and more. Let's see. So we measure how much this optimization can improve the loss. So theoretically, we'd have, I guess the grad would be, we have x, which would be gradient, and then y, which would be the loss from this model. So you see, okay, how much did this gradient actually help? So I guess it would actually be this output, this loss. The loss from the next output. Let's see. Measuring how well it reduced the loss. I wonder if it's the difference between the losses, or is it just loss? Okay, continue. Okay. Guide prob through the entire unrolled optimization process. So I guess you learn this, and you see how much. Okay. So you unroll this, and then you basically have this, a bunch of grads and a bunch of losses, and you sort of back propagate through time. So you do a big back propagation, and see which gradients moved for the loss more. Figure 2, page 4. Okay. Probably should start reading the paper, but let's just go through this quickly, just understand what we're doing-ish, and we'll get to the pictures and stuff like that later. Okay. So the LSTM learns how big the step should be, how to use momentum, how to adapt to different kinds of gradients, how to store memory across steps. Okay, so LSTM is learning how to make good steps. Let's read the experiment. One hidden layer, 20 units, sigmoid activation function. And tested it out. Different initializations, different architectures, different activations. Okay, so we did a bunch of experiments. Okay. So I think I understand the high level what it's doing. Now let's get into the more gritty details. I don't know where we are on this. Probably here somewhere. Let's skip to the. I'm sure the brief history is pretty interesting, but let's skip to, I guess, the real meat of the paper. Okay. Okay, let's continue. Okay. Let's see, the result is slightly. It's funny because it's optimal. Gradient descent for gradient descent. Let me just make sure. Yes, I'm sharing my screen. Last time I made a stream, I didn't end up posting it. I just forgot to share my screen, and that was, I'm assuming, really confusing for some people. No one commented. Not nice. Okay, so what's an optimizer? What does an optimizer? What's a good optimizer? Okay, so expectation of f Okay, I mean, I guess you're trying to minimize the expected loss. Yeah, I mean, that's how you define a good optimizer. Fair. Let's see. Okay. Earlier, we will take the update steps GT to the outputs of your current neural network N, parameterized by data. Okay. The weights will be. I know it's not theta, I just forgot what it was called. Theta with a line in it will be the weights. We'll have a model called M, and we'll output the gradient GT. And we'll be circling HT back into it. That's the current state. While the objective function in 2 depends only on the final parameter value for training the optimizers, it will be convenient to have an object that depends on the entire trajectory of the optimizations for some horizon t. Okay, so they're saying instead of just, here it's just optimizers expected. Yeah, I guess here's just expectation for one loss, and here they're like, okay, let's basically see how much each optimization step moved the loss, so we're going to unwind the entire process. So it's saying from t, and t is arbitrary, so it can be 10, 100, whatever it is. I mean, I don't like this. Like, wait, you're telling me, okay, expect value of the sum over wt f theta of t, where theta t plus 1 equals this, and gt and ht this. I mean, I sort of get it, but it's talking about the LSTM, or yeah, it's basically defining the LSTM and how it's taking in. Let's see if I actually understand this. Now it's taking in the old output, the new output, and yep. I mean, I know that made no sense, but I don't know how well I understand if I can't explain it. Let's read this first. Normal English. This means take a bunch of functions f task, sure, run optimization t steps on each task. Okay, so you're running the optimizer, let's say 100 times. Look at the loss. each step, add them up. So, okay, so it's similar to this. You get a loss for so we input, model, output, backpropagation. We're propagating the loss. So we can basically see how much. So each time we're getting a new loss. We're getting a loss here. We're getting a loss here. We're getting a loss here, and we're getting different gradients each time. So it's summing those up. Averaging over all tasks. Okay. The total is the score of the optimizer. Okay, so then that's how good your optimizer is. So all parameters plus, I guess this is just how the parameters change. How optimizer decides to update. This means so it takes the gradients, which we know. It takes it in HT. So I'm taking the gradients and I'm taking HT. Outputs, parameters, whatever. Oh, and its own parameters. Fine. GT updates the parameters. HT, the hidden state in memory. So the output is the new fine. Okay. So this is just saying the output is this. It's basically this. And we're basically saying we're summing over all of the losses, getting the average of all the losses from the entire optimization step, or the entire optimization steps. Checking. For people joining now, check out little break. Check out the new notebook mode. You can submit questions. You submit your solution from here. You could. I knew how to spell. I'd be like 10x engineer. You can run test cases here. We have 2 of them automatically preset. You can just write any other code. It's a lot faster for iterating and actually solving questions. So I'd say it's helpful. I'm probably going to solve most of my questions in notebook mode now. There's still some issues with it, which we're fixing, and I think there's still a spacing issue and stuff like that, but we're fixing it, we're making it better. So try it out though. Let me know if you guys have any issues with it. Let me get back into this. So here. Describe like using different weights can prove useful. Okay. You can minimize the value. Okay. So I'm trying to minimize that loss using gradient descent. Oh, I'm fine. Alright. Yeah, I feel like if we understand figure 2, Yeah, I feel like if you understand figure 2 and figure 3, I feel like we understand the paper. So I think we have, I mean, yeah, we have a paper review. I mean, if you're here, let's see how many people are. I don't think 0 people are supposed to join. 8 people, okay, cool. We have paper review on our Discord. I mean, if you're here, sort of, not a paper review, but paper understanding. Let's try and understand this. So, optimize Z and optimizer. Using gradients. So you have some model. Does some results. The model makes some predictions. You get the gradients. I'm assuming this is going to start off with 0, but you get some gradients. You feed it into the LSTM model. It will update the gradients, so make an update to it. And it will also pass HT1, the hidden state, into the new model. The new model will use the new gradients, compute the new model will make predictions, compute the new gradients. The new gradients will go into the model again. Same process, updates the parameters in the main model. Goes through this process again and again and again. And this is how it would optimize it. But I guess this tells you how it would optimize it, not necessarily how it would train it. By sampling a random function f defined by Pearson table. Oh, this actually tells us how it works better. We allow gradients to flow along the solid edges in the graph, but gradients along the dashed edges are dropped. Ignoring gradients along the dashed edges amounts to making the assumption that gradients of the optimized Z do not depend on optimizer's parameters. Let's see. So I guess we don't actually take in the gradients. No. What? Let's read that again. Assumption of the gradients. We allow the gradients to flow along the solid edges in the graph, but the gradients along the dashed edges are dropped. I'm assuming like it doesn't back propagate into here. Yeah, okay. I'm assuming it doesn't back propagate through these dashed lines, it's just the forward, like passing along the parameters. Okay. Okay. Explaining object number 3. One step of an LSTM optimizer, all estimates have standard parameters, but hidden state. So we're given the weights, it goes to a function, the function outputs. Okay, this is the full process. Okay. So we're given the weights are used in the model makes predictions, gets loss, the loss have gradients, so those gradients get passed to the LSTM. I guess this is weight set 1, so this is the full set of weights once. You get the gradients gets passed to LSTM 1. And then you take your old ones and you update it with the new ones, and that goes back and creates 2, and 2 goes through this process, and then you have LSTM2. Okay. I think I understand it. I don't know if you guys understand it, because my explanations are, you know, they're okay. But let's try and explain this. I mean, I think I understand being like I understand at high level, and I keep on saying that because I don't think I can implement this from scratch. I feel like that's my understanding. Okay, I could understand the idea, but I can't. But it'd be pretty interesting to make a question for this. Either a lab question. I don't know how. I mean, the lab questions I like to be open-ended. Can you solve? We have one optimizer question. Where is it? Design your own optimizer. We'll do pretty well on this. But can you train? I mean, also using access to numpy, so this would really be fun. So can you train this LSTM? I'm sure someone can. I don't know. You might be able to with enough time and patience, which I don't. I mean, I might have the time. I do not have the patience. Yeah, that'd be crazy. Okay, let's try and recreate this by myself. See if I actually understand it. So we have our weights. So we have weights. When I say W1, I mean the weights for the entire first iteration. So this would be weights 2, weights 3, dot, dot, dot. I'll be right back. And we're back. Sorry about that. Okay. We're getting to a good place. We're trying to understand the paper implemented ourselves. So, W1 is the weights for the first iteration. W2 is the weights for the second iteration, and so on. Each time, this weight are used in a model. Maybe we'll find this later. So, this weights are used within a model. The model creates a prediction get our prediction, and we get a loss. Correct? I mean, we do get a loss, but then that loss gets... Oh. Let's do this. We get a loss from that model. Predictions made with using W1. The loss goes to... We get our gradients from back propagating through there, and we get our gradients. Let's move this back. We get our loss. From our loss, we get our gradients. Okay, so we have grades 1, I go to a model, model makes predictions, gets lost. From the loss we get our gradients. I wonder how that looks. I don't know why. From our gradients. So we're at our gradients. The gradients get passed to our LSTM. I guess this would be LSTM school 1. The LSTM would look... An LSTM, we'll define that quickly. Again, model, we have arrow. We have an arrow, which would be the input, which is gradient right here. And we would also be taking in the hidden state, HT, whatever H1 in the first case. So this would be our LSTM. And it would outputs. Outputs this. We'll call 0 prime. And what will happen here is, pretty sure it's weights plus 0 prime in our case. Yeah, so once we get this value here, which is the prediction, it would be W1 plus 0, whatever, output from here. And this should be 1, it's the first time we're doing it. And then this is basically W2. W2 equals... Okay. So now we know what W2 is. And this... This W2 would go all the way back, and that'll be go. No. Okay, we're not. We got that W2 we just computed, we go all the way back here, and we go through the same process, and then we'll get W3, W4, W5, and so on. But how does that propagation work? How does the loss get computed? I guess these are take it in, make our prediction. I'm saying make our edits to the model. So I'm saying if you're back propagating through it, go here, here. Okay. And our loss gets back propagated through time, through the solid lines, not through the dashed lines. Okay. I think I'm going to take, I think I understand the main idea. I think we decided to do this week's book club relatively recently. I didn't have all the time to read this full paper. But I feel like I could contribute to the conversation. Yeah, okay. I think I'm gonna call it a day. Anyone have any questions or thoughts? I recommend solving today's daily challenge. It's relatively easy. Try using notebook mode for it. Other than that, I think that's it. Everyone, thanks for joining.